Edit. Hello, everybody. My name is Tolga, and I'm from FIU. I'm with the GluX collaboration. So we'll be sharing one of our projects on particularly a study on the beam asymmetry of gamma p goes to eta p with the GluX data set. So really, the actual experiment wants to understand hybrid mesons, actually doing an exotic hybrid meson search where exotic hybrid mesons not only would have a QQ bar and however many gluon structure, but would also break the naive quark model with the JPC example given there. And the collaboration seeks to study mass spectrum hybrids with respect to the quantum numbers. And these do decay to a lot of the lighter mesons, which include rhos, omegas, etas, and pions, pi zero rather. And in this work, we'll be focusing on the production mechanisms of the eta. So we're just going to be doing one meaningful contribution to an overall larger project. But that's not the only physics motivation that surrounds this research. So the eta is produced at GluX energies, which are about 8.5 GeV via meson region exchanges. And one of the polarization, so we have studies on cross-section, and I in particular am focusing on the photon beam asymmetry. And I'll explain why it's a photon beam asymmetry in a moment. And this value can be anywhere between -1 and 1, and that is a quantitative way to determine the production mechanism and what mesons are being exchanged to produce the eta. So if the value is 1, we have a natural parity exchange. So rho or omega is likely going to dominate the exchange process. And if it's -1, we have an unnatural parity exchange. So it'll be an H meson, axial vector meson. And another problem that surrounds this is a very similar meson, the eta prime, with a different quark structure. And understanding its production mechanism will also be interesting because it seems to be understood that, at least with this theory, that with this diagram from the JPEG model, that the ratio is generally 1 at low momentum transfer between the asymmetry of eta prime and the asymmetry of eta, implying, okay, the production mechanisms are similar. But if we do a ratio, we're trying to see if that ratio leaves 1, and then that way we'll discover some hidden strangeness exchanges. So this is really one of the big cells of doing this beam asymmetry study. And one of the other factors is that the JPEG prediction up to now is limited to low momentum transfer. So we want to expand our reach, and there is experimental data with a limited amount of data, and we're going to expand on that with the study. So prediction also shows an extra curve for some amplitudes in the eta process. So so there are 4 possible decay modes, but the one I have results to share today is for the dominant 1 eta going to gamma gamma. And the facility that is used to carry out the research, to carry out the production data is a GluX experiment in Hall D at Jefferson Lab in Newport News. Is that all the way over there? I have to stretch my arm out all the way. So through the Bremsstrahlung radiation, so CBAP facility launches electron beam at almost the speed of light. So at the Tiger Hall, through Bremsstrahlung radiation, we emit a linearly polarized photon that strikes it through the striking with a diamond radiator, and that goes incident on the experimental hall, where we have a liquid hydrogen target. That's where the P and gamma P goes to eta P kicks in. And a whole array of detectors track either the charged particles, or it'll receive showers from the photons that come out. And today, there's been quite a bit of discussion on those methods in the morning talks, especially in similar ways to how the EIC is going to be set up. But the GluX version is shown here, and the advantages are hermetic. It has a pretty full solid angle range acceptance, high energy polarized photon beam, and statistics have improved since the past result, which I'll mention a little later. So in order to calculate symmetry, we have to go through a mathematical process. Definitively, it's a ratio of the cross sections, but since we're choosing different polarization orientations, we're able to take a pair that are orthogonal to each other and cancel out a lot of these variables that do vary over the course of a run period, such as NT acceptance. And And gamma still has to stay because that's going to go in the flux ratio, and that'll even out like the inevitable number differences when you're running over long periods of time and running millions and millions of events. So so that's important. And we take the yields parallel and perpendicular to the floor and extract the beam of symmetry as follows. I do have to speed up. I spent a lot of time introducing this. So it's really to try to do a direct fit to this equation. So sample cartoon of the production plane and the polarization versus beam energy curve. Production schematic shows each individual event in each instance, and then from the polarization angles, the phase offset's fixed, and then we extract the sigma accordingly. So we need two key distributions. One's a mass distribution. Invariant mass distribution of 2 photons gives a signal which is eta, shown here. And the background is dominantly omega going to pi 0 gamma radiative decay. And I was able to simulate this with a rugged, at the time, Monte Carlo model. I've improved on this since. And then from there, we get yields that are important to consider when we do the angular distributions on phi, the azimuthal angle, where we get the peak and background angular distributions. And from the direct fits to sigma, we subtract the beam of symmetry. So this is what we call quad plot: parallel yield, perpendicular yield, the sum, and this ratio, which eliminates a lot of systematic variables, and then we get the direct fit of sigma from P0 right here. And we repeat this process for the peak and the sideband. And we correct it by another quantity called the dilution factor, which relies on these yields, the background and the signal yields in the yellow and the blue boxes. So taking the subtraction of, taking the ratio of those will give us a dilution factor, which allows us to correct for the beam of symmetry as well. And at higher T, even if there's like a little bit left over, it has such a, not only is the dilution factor really small, but also the sideband contribution is small. So the result is dominantly carried by the peak. And we kind of hit the climax here. Yes, I think I'm on time now. We hit the climax of the story here with the beam of symmetry result in the comparison to the past results and some modules. Leger model is really just, is kind of in place for like the pi 0 and is really like a baseline model. JPEG is the one that's of interest. It's been statistics limited to a low momentum transfer region. That's how the model was designed. But now there's expansions out there that we'll take a look at in the future. And then this has been run over 20% of the GluX1 data set in 2019, which is the blue points. And then in the pink or red, appears to be red on some screens, is this current work, which I'm able to show for low momentum transfer region, which confirms the past results in a sense. It verifies it and expands upon it with finer uncertainties. After that, we show for now the uncertainties only, but we fix that one as an arbitrary fix. But the general consensus is that it is very close to unity, but it does start to dip a little bit as we go into wider kinematic regions. So really, GluX is using this to aid in not only the exotic meson search, but also the comparison study with eta prime for hidden transients exchanges. And we show a very preliminary result for eta beam of symmetry that's expanding. Oops. What happened here? So the key thing that we accomplish here is that we're expanding the result up to with the data points so far up to 1.3, but we'll be able to expand up to 2 or even more GB per C squared. And future Monte Carlo analysis being carried out, and the systematic and the very tedious and long process of systematic checks are being carried out, and also we'll compare with the charge and I'll show results at some point in the future for those. And GluX acknowledges several DOE facilities, and that this work wouldn't be possible without them. So thanks, everybody.
Okay, questions?
These error bar are statistic error bar or propagated error bar? One level like that.
Yeah, error bars, they're on the order of like
Statistic or
statistical.
only a statistic?
Statistical so far. Systematic is being incorporated later. I'll let Brett go.
Can you go to slide 9? Talk about sidebands.
Yeah.
Actually, slide 8, whichever slide you're, yeah, there, this one. So you only do like a right side sideband? Did you like look at the left one as well of your A to peak?
It doesn't appear to be the left is expected to be, well,
Oh, it's log scale. Okay.
yeah, yes, log scale. The right is more significant, more is more useful.
Yeah. But what did you find like any like order of magnitude difference between like the omega asymmetries versus like what you find with eta? Like when you subtract away the sideband?
Yeah, because it does become about 25% of the peak at low T. But as T increases, that contribution dwindles. This is like an example with low T, where it's much more significant.
So assuming that sigma should be between data. So I got your data points if you go to slide 11. I'm assuming because you have
Yes,
uncertainty that goes below, but can you say why your averages are higher than 1 at low T?
likely that one came from an over subtraction of the sidebands. But that's been actually rectified. Yeah. Collaboration version.
Let's thank Dr. once again.
Physics content is very interesting. Data, so I think we'll also touch on data prime, T and data prime.
So the next one is by Shubham Sharma, who's going to tell us about GTMDs and particular F1 for the product. Okay.
Good afternoon, everyone. My name is Shubham Sharma, and I'm doing PhD under the supervision of Dr. Haleen Daya from Dr. B.R. Ambedkar National Institute of Technology, Jalandhar. The topic of my today's presentation is analysis of high twist GTMD F31 for the case of proton in the light front quark diagram model. So here is the outline of my talk. First, I will start with the introduction part. Then I will discuss about light front quark diagram model. This is the model which I'm using, then its input parameters. After that, I will discuss about GTMD correlator results and then summary. So after the discovery of proton and neutron by Rutherford and Chadwick in about 1931, it became clear that proton, neutron, and electron are fundamental particles which cannot be further divided. But this is soon busted by Gell-Mann and George Wick, which when looked clearly says that proton and neutron are same in all aspects if the charge is ignored. So here comes the theory of strong induction, which we called as QCD. The foremost problem of QCD is to understand the hadrons in terms of quarks and gluons. So we are going to work with high energy. So here is in special theory of relativity, we have 4 coordinates, which is 1 time coordinate and 3 space coordinate. So time and space are not invariant quantities, rather space-time collectively is an invariant object. So here we have a light cone. We have 3 different types of reason depending upon the velocity of the particle which we are studying. So we are going to work with light cones. Here we have 3 different types of dynamics, which are instant form, front form, and point form. We are going to work with front form. Why so? Because it is an ideal framework to describe theoretically the hadronic structure in terms of quarks and gluons. It has a simple vacuum structure. That is, no particle antiparticle can pop up by itself. And we knew that a dynamical system is characterized by 10 fundamental quantities. And in this case, we have 7 out of them which are kinematical. And third one is it has a simple dispersion relation which does not consist any scalar effect. So we have 4 coordinates, and when we combine time coordinate with the longitudinal space coordinate, we get light front time and light front longitudinal space variable. So, and the remaining 2 variables, when we combine, we get the transverse variable. Similarly, we can define longitudinal momentum and the light front energy. So before coming to distribution functions, how we came to know about the distribution? We came to know about the spatial distribution through elastic scattering of charges and current. We came to know about spatial through momentum distribution by using deep inelastic knockout scattering. So here are different distribution functions. Here are different distribution. Here are different distribution functions. This is what we call as GPCF. This one is better. So this is GPCF. This is generalized pattern correlation function. When we integrate over the light front energy, we will get GTMD, which is generalized transverse momentum distribution. Today, I'm going to discuss about GTMDs. And when we apply the limit del equal to 0, del is what we call as the momentum transfer between the initial and the final state. We will get TMDs. And when we integrate the TMDs, we will get PDFs. So today I'm going to discuss about TMDs and PDFs. And here is a chart of all the different of distribution function. X is the longitudinal momentum fraction carried by the quark. T pup is the transverse momentum of quark, and del is the momentum transfer. Okay. So yeah, the light front quark dipole model. So this is a model which I'm using. In proton, we have 3 quarks. So what we say that when a scattering happens, it happens with 1 quark, and the remaining 2 quarks will act as a spectator. So from where we have quark and a diquark model, and this model consists that proton has a spin flavor SU4 structure, and it's made up of isoscalar scalar diquark, isoscalar vector diquark, isovector vector diquark, and it is written something like this. Okay. So in this frame, the average momentum carried by the hadron is given by this, and this is the momentum transfer between initial and the final state. So the momentum of quark and a diquark is given by this. So this is the Fock state expansion for the case of scalar diquark, and yeah, this is the helicity of quark. This is the helicity of diquark. This is the longitudinal momentum carried by quark, and this is the transverse momentum carried by quark. That's how we write it. And we are going to I will discuss about these files later. And these are the light front wave function for scalar diquark. Similarly, we have light front wave function for the case of vector diquark, and they are expressed in the form of same wave functions phi. So the wave function phi is adopted from light front ADS QCD, and the parameters A, B are included in this model. Right? They are fitted by using Dirac and Pauli form factors. We will discuss about this in input parameters. So these are the parameters. Okay. So these are the parameters of the model. Let me skip this one. We are taking quark mass to be 0.055 giga-electron volt and hadron proton mass to be 0.938 giga-electron volt. Coming to GTMD correlator. This is GTMD correlator, which we get by integrating across the light front energy. And this is the final state of hadron. This is initial state of hadron. This is the quark field operator, and this is the Dirac matrix. We calculate different GTMDs depending upon what value of Dirac matrix we are using, and this is Wilson line. So let me clear that we are taking Wilson line to be 1, and whatever we are getting is just corresponding to Wilson-Wilczek approximation. So these are the dynamics like average momentum, transverse momentum transferred, and same thing this is the parameterization. We are focusing on this GTMD F31. It is corresponding to twist 4 TMD F3, and it has a partner in twist 2 TMD, which is F1. All are discussing about it. So results. So this is the result for my TMD for up quark and for the down quark. See, this TMD in twist 4 is relating to twist 2 TMD like this, and this is just a Wenzhura-Wilczek approximation, and this relation holds in our model as well as in some other models like light front consistent quark models and some other model. And here we have discussed the average transverse momentum in light front quark diquark model and in light front consistent quark model. And here we find that average transverse momentum is found to be in close agreement, although the average scale transverse momentum is not so close. Okay. So here are the plots of GTMDs. So when we apply in GTMD, we have 3 variables like X, T perp, and del. So we can't discuss about them simultaneously. So we will fix one and discuss about the 2 at a time. So for first, I have discussed the TMD limit. When we apply the TMD limit del equal to 0, so then we get this kind of plot. This is similar to F1 plot, which we are getting in twist 2, but it has a slightly less amplitude. And here it is like we have maxima, it's around 0.3x, which is generally happens at F2 TMD. So when we consider that there is some momentum transfer in the process, then we get this kind of plot, like we are observing a high amplitude at a low x. And yeah, it is difficult to analyze this, but we can say that like at very low x and at very low x and low del pub, and similarly at very high x and high del pub, we are getting this distribution. So yeah, that's pretty much everything. So when we can plot this with respect to one variable at a time, keeping the others fixed. And yeah, that's it. Thank you.
Thank you. Questions or comments? Yes.
When you had a relation between
Yeah.
with a twist 2 team, you said,
Yes.
but
Yes.
the GTMD is twist 4. So
Yeah.
how can you relate it? I didn't know you could match
Okay.
twist.
Okay. We have calculated this GTMD and we have applied TMD limit. So we get the TMD for twist 4. Like similarly, we have calculated twist 2 TMD in this model. And we have then we say see, is there any explicit expression relation between those two? And from that we get this.
Okay.
Yes.
I understand we are calculating GTMD, and by doing a Fourier transformation of the delta purple, you can get to regular distribution, right?
Yes, we can calculate the Wigner distribution, but there is slightly problem at high twist because this is not we can't distinguish between like what is the polarization of hadron and what is the polarization of quark at high twist. At lower twist, it is simple that quark is unpolarized, longitudinal polarized, and transversal polarized. At high twist, we know that this GTMD is corresponding to the unpolarized hadron. But what is quark polarization? It is not sure. It is a combination of different polarizations, so we can't do Wigner distributions at this twist.
My question is that, so by doing Fourier transform, you will get regular distribution, and regular distribution give you the distribution in both momental space and coordinate space, right? So, but this always make me confused because according to quantum mechanics, quantum principle, you cannot have the kind of distribution that is both in momental space and coordinate space. Can you
As far as my knowledge is concerned, that uncertainty principle is followed there, that we have like momentum distribution along different variable and like something like this, that it is followed. Uncertainty principle is followed there. I have read about it, but I don't know exactly how to do it.
Wait for barbecue. Discussion during barbecue. So here's the question. We heard that Wigner distribution is a 5-dimensional distribution. Describes position and transverse momenta of the quarks. But Heisenberg told us, and we know position and moment at the same time. So how come these distributions can exist? The answer is they can exist, but why? We'll see at 5 p.m. Okay. Anyhow, go ahead.
Yes, using the light front coordinates, is your entire calculation done in holographic light front QCD? Like
Yeah.
no kappa.
I have done all calculations in light front coordinates.
No, but like, are you using the ADS QCD?
Wave function. Yes. Yes.
Thank you.
Right. Yes, thank for calculations. Those computations are quite complicated. Thank you. All right, so we switch gears here. So let me first pull your presentation. Right, so
Okay, so I'm Nisha Chahal and I wait a second.
this is great. Magnetic field and volume of susceptibilities of concerned charges. For the Earth.
Okay, so I am from National Institute of Technology, India, And a lot of people work here related to EIC, GTMDs, TMDs and all that. It's very different work than this. So the question is why I'm here. So basically because I'm the last year of my PhD and this is a new field and just to explore the new field and the new opportunities. So I'll give you insight of what I do. Okay, so I'm working on, in this, I'll be talking about the impact of finite size and the magnetic field on the QCD phase diagram. Now, so this is a very beautiful diagram we have in the high energy physics, which is the QCD phase diagram. Now, here, the point we talk about the vacuum where it is 0 temperature and 0 baryonic chemical potential. And the position, the early conditions of early universe is said to be at very high temperatures and 0 baryonic chemical potential. And now as we move along, so these are the various experiments listed over here working in the different temperature regimes. And as we move further, we have this point of nuclear matter, where the nuclear matter is said to exist. And this first order phase transition line separates the hadronic gas phase and the quark-gluon plasma phase. So we know that here the quarks are confined, and this is the phase where quarks and gluons are in the free state. Now, any question? Okay, now this first order phase transition line ends at a critical point, and further than this, we have a crossover. So, the crossover means the smooth transition of the thermodynamic properties. But when we talk about the first order phase transition, the properties like pressure, entropy, and density have a sharp change. So that is how we distinguish this crossover from the first order phase transition. Now, the question is, what is the nature of this critical point? It's a first order, it's a second order, it's a crossover, and what exactly is the position of this critical point? So now moving on to, so in order to calculate the position of the QCD critical point, we calculate the fluctuations of conserved charges. Now, as you know, the conserved charges are baryon number, strangeness, and charge number. So when we go from one phase to another, so definitely there will be a change in the degrees of freedom. And so we will have a sharp fluctuation in our conserved charges. And that is what we are trying to calculate. Now, in order to calculate that, we have this chiral SU3 quark mean field model. So in this model, we are considering quarks as the degrees of freedom. And chiral because the model is based on the chiral symmetry breaking basically. And mean field basically means we consider the particles behaving under a mean field potential, and then we study the interactions. Now in this model, so in this model we have different terms. I have not written the complex form of the Lagrangian. So the first term is for the free part of the massless quarks. Basically, that means without any interactions, we are taking the quark term, and this basically includes the kinetic part of the quarks and the mass term. Okay. And next is quark meson interaction terms. So these terms are basically because we consider in this model we have scalar and vector fields. So what do is we have quarks, we have scalar and vector mesons, and we study how they will interact with temperature and density. Now these the scalar fields, we have sigma field, zeta, delta, and Dalton field chi. And for our vector fields, we have omega, rho, and phi fields. So I mentioned the different terms. Now moving on, by using our statistical physics, we know from the Lagrangian, we can go to our thermodynamic potential. So by using all the mathematics, we come to the thermodynamic potential density defined. So in this thermodynamic potential density, the main terms is this EI star. So EI star basically represents the effective single particle energy of quarks, because this particle energy will be modified due to the different fields. It can be written mi star plus k square, where k represents our momentum, and this mi star is the effective mass. This effective mass gets modified due to the scalar fields, whereas this nu I, which is the effective chemical potential, the effective potential gets modified due to these vector fields that are omega, rho, and phi. So we are taking the contribution of scalar and vector fields combined to see what will be the modification in our susceptibilities or our conserved charges eventually. Now moving on. This model, the chiral quark mean field model, does not include we are not able to define the deconfinement very well. So for that, we include Polyakov loop, and Polyakov loop basically is an order parameter, and it is defined by using the Wilson loop. And by using the Polyakov loop in our model, so we have this correction where the total Lagrangian minus this Polyakov loop variable. Now there are different forms of Polyakov loop that we use in different theoretical models. For my work, I have used this logarithmic form. Now, some people ask that what will happen if we use different forms of Polyakov loops. So there's a story behind this, how I discovered the different forms. So what happened? I submitted a paper, first paper, and I was comparing my susceptibilities, and when I changed the values of Polyakov loops, I had a better fit with the data. So basically, in the theoretical models, we always try to fit the parameters according to the latest QCD data to get more of the known values. For example, we know what is the quark mass, like U, D, or we know the pion masses. So we try to fit our models according to the known quantities to get the unknown quantities. So that is how we decide which Polyakov loop is better for us to fit. So now moving on, how we include the magnetic field and volume effects in our model. So first of all, let me define what is volume effects. So basically here, when the collision happens, usually in our model, we take the momentum integration from -infinity to infinity, or we can say 0 to infinity, and we are summing over all the momentum states. But in lattice QCD we were studying, so they define a volume, a cubic volume. It can be done in many ways. So I am considering a cubic volume, and in which we have a defined momentum as soon as the collision happens. So what I do is I put a lower momentum cutoff, that is P minimum is equal to pi by r, where this r gives r cube, the cubic volume. And next, as we know, when the magnetic field comes into the picture, and there's Lorentz force. So due to this Lorentz force, we will have Landau levels. So these levels are included as 2n plus 1 minus gamma, where n is the principal quantum number and gamma is the spin quantum number. So considering this and adding this to our model, we get a defined quark and anti-quark interaction term. And by this, we can study how our model will evolve with the inclusion of volume effects as well as the magnetic effects. So these two are separate things. I have not studied them together, differently. So moving to the result. So how do we know where is the position of the critical point? So as I said, whenever we have a critical point, there will be abrupt change in the properties. So sigma basically is a scalar field that I have plotted. So at different values of first, I have plotted for magnetic field equal to 0 and r equal to infinity. Basically, this is the ideal situation we take in our models, where we take the infinite size system and magnetic field as 0. So as we can see here, with increasing baryonic chemical potential, mu b is baryonic chemical potential. So this peak gets shifted to lower values of temperature. So this shows that how our boundary is getting modified with different baryonic chemical potential values. Now, as we move to finite value of size, this gets shifted to higher value of temperature. So higher and lower doesn't give us the insight. This basically means, will we have a boundary that will be more of first order phase transition or more of crossover? So keeping this. So this is the ultimate QCD phase diagram plotted using all the dynamics. So here, this line shows the chiral phase transition of U and D quarks, which is plotted by taking the sigma field in consideration. The above lines are for strange quark, and these lines here are for deconfinement. So basically, we plot separate phase transition lines depending on S quark, U and D, and for deconfinement through our Polyakov loop variable. And what we get is, for different values of magnetic field, we can see that we will have a crossover because this point is getting shifted to lower values. So eventually, as the magnetic field increases, we will have only the crossover. But in case of decreasing volume, this changes more to the first order phase transition, and less of the crossover. So that is the main finding of the work. And these are the plots for our fluctuation of conserved charges, where we can see as we reach to this value, say this 160, which is predicted by our latest QCD, that our crossover at zero value of baryonic chemical potential is near 160 MeV. So we get a fluctuation there. So that is what all these curves show. And for validation in these models, we have two things. One is we can compare with the start data, or we can compare with latest data. But I don't have the direct to get the data and compare with that. So I compared with that QCD and I got a good fit. And this for charge number. So in summary, again, our point gets a critical point shifts to lower values with the increasing magnetic field, and it shifts to higher values with decreasing system volume. So thank you. Yes. It's an order parameter. And we basically this is through the Wilson line, and this is an order parameter to include the deconfinement in our model. So
Does it have any connection with Polyakov action? And because I know if that is correct information, this Polyakov action was first introduced in QCD.
yeah.
That it was sort of a bridge to string theory, as I understand. So it's just if there is some connection to this Polyakov loop to Polyakov.
I don't know, but I know the background of this one, that it is through the Wilson line. Yeah. So, yeah, maybe I'll check that.
Okay. Thank you. Questions? So Nisha was asking herself, what am I? She spent the whole week, right? It's like, what am I doing here? Now here's the answer. The whole idea of the school is to broaden the participation of students and researchers in our field. Now, of course, it's not a surprise to you that heavy ion physics that is studied extensively at proton machines, relativistic heavy ion collider a few months away, plays a very important role in understanding of this plot or the critical point. And QCD is a very important task of these types of machines. Now, the physics of heavy ion physics plays also quite important role towards the EIC. So next week you will have answer to why you're here. We will have lectures from Raju Venugopal, who will touch upon heavy ion physics and phase diagrams, and then you'll feel you are a fish in the water, not outside the water. So don't doubt your being here. You're very welcome. That's the opportunity for all of us to broaden our views. The fact that you actually showed your result is quite admirable, because now it's an opportunity for us to learn something new. So thank you. Right. So, yes, the upper is your
The upper is what?
is the laser pointer. It's not the laser pointer. It's like a.
Oh, okay.
Oh, where did you find this? This is a very dangerous thing, you know. And if you press the button here, it will stop the screen.
Oh, I pressed it already.
You press it. Okay, that's better. So this will be the laser. This will be after I press it through. Let's go forward.
So this is all this.
If you reflect. All right, so Eric is going to tell us about the other mechanism for transfer single spin asymmetries in Manzura-Wilczek approximation.
Okay, hello everybody. My name is Eric, and today I'm going to present you my work that I had been doing with my PhD advisor and my collaborators. And the topic is other mechanism for transfer single spin asymmetry in Manzura-Wilczek approximation. Okay. Before I start, I must tell you that once I tried to open with a joke. Yeah, I will never do this again. Never. Okay, so my goal is for you today to understand everything what is in the title and provide you with our results. Okay, let's go. So first, of course, the main thing in the title is transfer single spin asymmetry. So what it is exactly? When you have a collision of two particles, when one of them is polarized, one is meaning of this single. After the collision, you will have an asymmetry in final state. And this asymmetry is actually observable, and you define it as a difference of particles that go to the right, to the left, right and left of what? Well, to the plane which is defined by spin and the collision axis. Okay, so we want to find out why this happened, and this is the goal of this. And I want just to tell you that whenever you do calculations involving spin, you will always have an imaginary unit in the Dirac traces. So different approaches to finding this asymmetry is actually a different way to find extra I, which will make cross-section real. Okay, I will just give you here some experimental data. This observable has been measured and it exists. I won't go into details of how it was measured. I only want you to focus that it was measured in some region of X that it depends on nuclear number. So it depends on A. So what that may hint us that in this actually transfer single spin asymmetry can be a good way maybe to probe saturation in collisions. So in what we were doing, we were actually trying to find spin asymmetry using color glass condensate effective field theory. So in this slide, I will present you what color glass condensate really is. So you know, all of you, that on small x, gluons dominate in hadrons. So partial distribution functions of gluons grows rapidly when x goes to 0. But how much will it grow? I mean, if you have, it can go to infinity, because if you have infinite number of gluons, you wouldn't have unitarity of cross sections. So that means that at one point, those gluons need to start to recombine. You know, there is a vertex of two gluons into one gluon, and when this process become important, it's defined when decay width of gluon, two gluons to gluon becomes of order 1. It's known that decay width is proportional to x over q squared, sorry, and the q at which this becomes of order 1, it's called the saturation scale. And in this regime, hadrons are populated by gluons, you know, maximally. Okay, and then when you have a collision of two hadrons, and now imagine one parton from one of those hadron entering this field of a lot of gluons in another hadron. It will actually experience a classical field. Why is it classical? Because you have a lot of gluons, you can approximate that it is a classical theory. How to find this classical field? By solving Yang-Mills equation, classical Yang-Mills equation. Now, after you have this classical field, you need to solve a Dirac equation of this quark which propagates in this classical field. After you solved it, I mean, you need to find a Green's function or a propagator. You find an effective propagator of quark which travels in the effective field of nucleus. And okay, this is basic idea of color glass condensate. Just to mention those 3 letters, CGC. C is of course for SUT charge or color. C as a condensate, a lot of gluons, and glass. This is the most important thing. Gluons that are on lower X since the time dilatation, they see gluons on higher X as frozen in time. And this is actually a property of glass from solid state physics. Glass is a material that on short time scales acts as behaves as a solid, and on long time scales behaves as a liquid. Okay, this is basic idea of gold glass condensate. And yes, one more thing, nuclei will saturate at higher X. Okay, nice, exactly as I planned. Okay, our mechanism, aka other mechanism, it's not the first mechanism that tried to explain single fin asymmetry. It was a lot of work has been done regarding this. This is just one ATQS mechanism where they were using, this is a work from 2016 at Hart et al. They were using ETQS functions. ETQS functions are correlators of two fermions and gluon strength tensor. Okay, now let's go to the other mechanism. It was first introduced in 2012 by Yuri Kuchegov and Michael Sievert.
No.
Sorry?
Not.
Matt. Okay, Matt Sievert. I'm sorry. They were trying to calculate asymmetry in collision of quark with nucleus, and they were also using color glass condensate effective theory. Okay, first I want to introduce this object. This called is dipole distribution function, and of course it will come up in CGC calculations, because in CGC calculation you will have Wilson lines as a product of Young-Mills equations, and they will be in the propagators of our partons. And when you have amplitude square, you will have trace in color space over those Wilson lines. And this dipole line distribution can be split into the real part, which is called Pomeron, and imaginary part, which is called Oderon. It was already introduced today what Pomeron is. Oderon is just charge conjugate. You can imagine this as an exchange of free gluons in color singlet state. Okay, and they found out that if Oderon can supply necessary phase, if you remember from my first slide, you need to have a phase, and they calculated this at the parton level. Okay, I want to now bother you with the details here. They found, okay, there is this I, okay, and another I will sit in the Hart factor. And they found out that AN has some nuclear dependence. What we were doing, we were colliding protons with nuclei. First, what we need to do is write down a full cross section, polarized cross section. This formula is written up to twist 3, which means we consider only these diagrams. And okay, I am out of time, so what we did, we considered one approximation. We took only twist 2 part of this twist 3 cross section, and this twist 2 part can be written like this. So this GT distribution function, which is connected with helicity distribution inside a parton, has twist 2 part and twist 3 part, and we neglected twist 2 part, and this was our master formula. And now this S0 can be calculated in perturbation theory. You know, this S0 is actually what happens here when you take one parton. This is a distribution function. Okay, and now is all phenomenology. You can take a diagram, and of course you will need interference of amplitudes. If you have square amplitudes, you won't have I, so you need to interfere diagrams. And this is, for example, one diagram that contributes to the asymmetry. And when you extract X0, you get this formula. Those 2 parts are off diagonal, they will contribute. And then, of course, this is now just calculation. This trace over here, which is an artifact of previous formula, can be, after some manipulation, can be put in this form. And this is now just the hard part. And this term over here can be written as a dipole correlator. And now just a few calculations lead us to this final formula, where we have this in hard factor, we have combination of those 2 of this vector. But now, if you remember from here, we have derivative over K1 times S. So we will have only one vector, Q minus ZK1. See, this is same vector in pair in this combination. This means that we cannot form cross product. This is much better written in our paper, but this is just intuition. You can't have a cross product between outgoing state and the spin because there is no enough vectors in this. So basically what this means that there is no polarized cross section in this approximation. We also considered virtual contribution and same conclusion was there. So there is no cross section neither for virtual contribution, and also gluon initiating channels leads to the same conclusion. So this is very depressing. We see that there is in this approximation there is no cross section, so that gives us a couple of things to do now. We can go beyond next to leading order. Yeah, one more thing. There is no leading order in this because you only have a square diagram which don't have spin asymmetry. Okay, so and we can go beyond next leading order, or we can go beyond Andrew-Leverage approximation. And I must say I already started calculations beyond Andrew-Leverage approximation. Thank you very much for listening.
That was really nice. Thank you. I think I missed something. You were saying the Pomeron is like a 2-gluon color singlet.
Yeah,
The Autoron is
it's
also-
it can be considered as a free one.
Okay.
It's a odd gluon exchange.
And then the Autoron, is that also a color singlet?
Yeah, it's also like in it's also
How many gluons?
it's free in lowest order. Yeah.
Yeah, Eric, thanks for this presentation. I just have a comment on the transfer single spin asymmetries
Okay.
for Phoenix. Yeah. So there you could actually, if you want, update the
You mean on the slide where?
yeah.
Okay.
Yeah, just there. So we have the recent result where we tried to plot single spin asymmetries as a function of the transverse momentum.
Okay.
So yeah, you would want to look at that.
Okay.
It's we published in 2020. This is 2023. Yeah, in 2021.
Okay.
Yeah. So you'll find that the single spin asymmetries in PP collisions, that is actually right asymmetry. So you find it's around 5%.
Okay.
Yeah, and then for proton heavy collision, that goes to about 10%, and it's a left asymmetry. So
Okay.
it's kind of a flip,
Yeah.
which we explained in terms of a combination of EM and hadronic interactions.
Okay.
So
I will sure look at it. Thank you.
Thank you.
Questions or comments?
Yeah, just to say, this also isn't connected to EAC because I observe PA collisions. So. Yes.
Well, first of all, at the IC, you can still talk about diffraction contributions to Pomeron or Roderon exchanges are quite important. So talk about quasi-elastic production. So if just a comment, if you still ask yourself why it's glass, okay, don't worry. Next week we will have lectures from person who actually invented color condensate. Then Eric mentioned Matt Sivak, who was one of our lecturers during one of our schools, and he's actually at BNL right now this summer. So should we ask him to come to one of our discussions?
Yeah,
sure. Yeah.
Absolutely. Yeah, I'll do it. I'll send him a message, and so you'll meet also Matt, who was our lecturer next week. So I'll tell him perhaps then we start with small X physics, invite also everybody who's related to this subject, so we can have discussions.
Okay.
Thank you so much. This our last but not least presentation. Julian, you have 2 slides.
Yeah, the non-handout slides.
You want handouts?
One is labeled handout and the other one.
Let me do this. Let me just open.
That's the handout version now.
What's that?
That's the handout version.
It's the handout. Yes, I was doing.
No, the other one would be better.
You don't want handout?
No, no,
No, the other one.
the
Okay,
other one.
sorry. Sorry.
Yeah, the handout is just without overlays for you
Okay.
to look at later.
Let me just prepare everything.
Okay, great.
Okay, so Julian is going to tell us about the massless single off-shell scalar box integral.
So, hi everyone, I'm from Germany and I will tell you about our calculation of this loop integral here. If you don't understand the title right now, that's fine. I will explain it later in the talk. And it's based on work I did together with my colleague Fabian. Okay, so here's my outline. First, I'll give you a brief introduction to loop integrals and dimensional regularization, which we will then need for the actual work. And in the end, I'll give you a conclusion and a brief outlook for generalizations of our result. Okay, about loop integrals and dimensional regularization. Okay, so I guess you've all seen Feynman diagrams, and using Feynman rules, these can be translated to mathematical expressions for scattering amplitudes. And the Feynman rules tell us that form momentum is conserved at each vertex. I'll have to sit here. So, yeah, so if we have momenta K1 and K2 flowing into the diagram here, then this virtual photon here must have form momentum K1 plus K2. So form momentum is conserved. Now, we could also have loops like this in our diagram, and momentum conservation allows for any momentum L to flow around the loop. And we should take all these possibilities into account. So we sum over all possible loop momenta via this integration, and that's how we get a loop integral. Okay, so let's look at a typical one loop integral. So the denominator will be of this form here with loop momenta and the mass of the particles. So that comes from the propagators. The Feynman rules tell us to associate the lines in the Feynman diagram of the loop with factors like these, and they all have denominators like this. So that's what our denominator will look like. So this I0 here is a small positive imaginary part, and it preserves causality. We will use it to establish the imaginary parts of our loop integral. And there could be some dependence on the loop momentum in the numerator, but actually we can reduce these tensor loop integrals to scalar integrals, which have no dependence on the loop momentum in the numerator. So we only really need to consider integrals like that. And this box integral we consider is of this form. Okay, so let's first look at a brief example. This bubble integral here with two propagators looks like this. And for very large loop momenta, it would behave like this here, which gives a logarithm once integrated. So it diverges logarithmically for large loop momenta going to infinity. This is a problem. Like, we can't compare infinity to infinity. So we must parameterize this divergence, which is known as regularization. And then we will have parameterized the divergences. We can add all the contributing diagrams, and we know how the infinities add up. Okay, how do we parameterize these divergences? So the method of choice is to change the number of space-time dimensions. So originally we have the physical 4 space-time dimensions, but we can make the space-time dimensions a little smaller. Like, we make them smaller here with positive epsilon. And then this loop integral doesn't diverge logarithmically anymore, but instead it behaves like this, which is finite for large loop momenta and positive epsilon. So we've parameterized the divergences, and they will then manifest themselves as poles for epsilon to 0. So we will first parameterize all of our divergences, and then once we add all our contributions, various diagrams, we hope that these infinities vanish. And yeah, we can deal with this. Okay. Now with this introduction, we can move on to the integral we're looking at. So why are we motivated to look at this? So at next to leading order, DIS, electron-positron annihilation, and Rayleigh all feature the box integral in the corresponding Feynman diagrams. And all these integrals have a single off-shell gauge boson, which here is shown as a photon, and this has non-zero mass. So that's the single off-shell in my title. And we can neglect light quark masses in the high energy limit, so we need to only look at the massless box integral. As mentioned, we can reduce tensor loop integrals to scalar integrals, so that's the scalar in my title. Yeah, and basically this integral is available in the literature, but the results are not that user-friendly and not established to all orders in epsilon. So what we want to do is give an all-order epsilon expansion, which is valid in all kinematic regions. So you can just plug your kinematic variables in and get a result, not a lot of work required. So for example, Q squared has different signs for all of these processes and the Mandelstam variables too. And we just want our result to be usable for all of these processes. And we also want to give real and imaginary parts explicitly, so you can just read them off. Okay, so here's the loop integral we're looking at. As mentioned, we work with massless propagators, no masses here. We consider this particle here to have non-zero momentum squared. We work in dimensional regularization, and we keep this I0 throughout the calculation, which allows us to establish imaginary parts. Okay, so here's the loop integral again. How do we calculate this? So the standard way is to apply this formula here, which is known as Feynman parameterization. And then this transforms the product of propagators into a sum of propagators. And then we can shift the loop momentum and get an integral of this form, where we have introduced Mandelstam variables. And there's a formula to evaluate integrals of this form, which is derived in quantum field theory lectures, but you can just believe me, they are always evaluated via this formula. And now we are just left with the Feynman parameter integral here, and we have to solve this one. And up to here, this is pretty standard procedure for any loop integral. It's not special to the box. Okay, so how do we proceed with our box integral? So the Feynman parameter integrals can actually be decoupled through this substitution here. And then the eta integrals factorize from the psi integrals, and we can immediately evaluate the eta integrals. So we just have two integrations remaining. And we can also factor out this term here, and then our integral only depends on two-dimensional variables, which is an improvement from before, where it depended on three-dimensional full Mandelstam variables. Okay, so, and then we took this integral and evaluated it. So that involves some work, which I will not go into in this talk. And in the end, we find this epsilon expansion. So we can see that our loop integral diverges like 1 over epsilon squared for epsilon to 0. So that shows us that the box integral itself is not a measurable quantity. It just shows up in the amplitudes. And it's very easy to read off real and imaginary parts depending on the sign of the Mandelstam variables. We provide an all-order epsilon expansion. So the calligraphic F function here is given in terms of its epsilon expansion. And these terms here and the exponential are really easy to expand. So you get an all-order epsilon expansion from this. And our result is usable in all kinematic regions. So for real values of the kinematic variables, you can just plug your kinematic variables in and you get back a result. So now you might wonder what this function here is. Those are so-called single value polylogarithms. They are basically just a linear combination of logarithms and regular polylogarithms. And here we have plots of the first few single value polylogarithms, which show that you can plug a real number in and you get back a real number. And they also have some nice properties. Nice is they are bounded, so they don't diverge anywhere. And they satisfy clean versions of the functional equations of the regular polylogarithms, so it does make sense to label them polylogarithms. But like this is very technical, it's enough to know that they are just defined as a linear combination of other functions. Okay, and with this, I've arrived at the end of my talk. So we've established an all order epsilon expansion of the massless single off-shell scalar box integral in terms of these newly introduced single value polylogarithms. Real and imaginary parts are given to all orders in epsilon, and our result is easy to use and hopefully quite user-friendly. Now, we found out that our result can be easily generalized to two non-adjacent endpoints of the light cone. So that's like if you have your box, two particles on opposite corners have a mass that's not zero. But for further generalization, additional methods would be needed. And a good starting point for that is an integral representation found by Tarasov in 2019. Okay, thank you.
Thank you. Questions or comments?
Is this analysis specific for d equals 4 or for any dimensions?
I didn't understand.
Is the analysis specific for 4 dimensions or for any dimension?
It works for any dimensions because we established the all order epsilon expansion. So epsilon can be anything. Well, a real value. It's a real parameter, but it's not specific to 4 dimensions. Daniel?
So a single value refers to not having a branch cut?
Yes, exactly. So if we go back to these single value polylogarithms, the regular polylogarithms have a branch cut along the positive real axis greater than 1. They inherit this from the regular logarithm. And the single value polylogarithms don't have this branch cut anymore. And this branch cut would be problematic because we want to be able to just plug our kinematic variables in. And if we have a branch cut there, we don't know which side of the branch cut to choose. So the single value polylogarithm save us.
Questions?
And your fourth number slide,
Which slide?
fourth number where you have the Feynman diagram. So do you know the probability of this process in percentage? That let's say first process happened, let's say 50% or 60%, and so do you know this like in percent, or you can calculate percentage of these processes?
You mean like, can I calculate with
Yeah.
which probability they have?
How much? Yeah, this process had.
I mean, I could calculate it, but I didn't do it. So like, this is a higher order correction to this process. So I would guess that this yields a smaller contribution than this one, but it could be larger as well.
Way to calculate higher orders, for instance, proton, go beyond.
Yeah. So
leading order to next to leading order. Is it the final goal of your project?
yeah, the goal of my project is to calculate the CIDIS cross section at next to leading order. So the box integral shows up for me here, like.
So this diagram coming into in the does it have something with the hadronic part or the leptonic part? Or?
So well, this is on parton level, but this part here, these would be, for example, electrons. So this would be the leptonic part, and here you have the partonic part.
So it is incorporated into the distribution function, something like this.
The distribution, like this is all on parton level, so this diagram would be multiplied with distribution functions.
I understand.
Clarify, and then you have to use next to leading order parton distribution functions, and therefore at that point we'll be able to use the same precision of extraction from semi-inclusive plastic scattering for proton scattering. So that's actually it's going to be a breakthrough in our understanding of in terms of precision of parton distribution functions. Thank you so much.